In section 4.3, we're going to continue to work with the mean value theorem. We're really going to be applying the mean value theorem. We're not going to be working with it directly. And by applying the mean value theorem, what I'm hinting at is this. We're going to look at what the mean value theorem says about a function when it's increasing. Now, if a function is strictly increasing, that as you move from left to right, it's just going to keep on getting bigger and bigger. It's not going to pause. You're not going to have a horizontal tangent anywhere. It's going to keep on getting bigger and bigger. If the function is increasing in this interval, let's look at a couple things regarding this quotient. Yeah, there's some point in between that's equal to f of b minus f of a over b minus a. But b minus a, that always has to be a positive number. What about f of b minus f of a? Is that going to be a positive number or a negative number in this interval? Assuming that f of x is an increasing function. Is that going to be positive or negative? When I subtract, say this is 10, this is 3, when I do top minus bottom, am I going to get you're going to get a positive number. So when you have an increasing function, the derivative has to be positive. Always. So f prime of x is going to be greater than 0 whenever f is increasing. Whenever f of x is increasing, you're going to have a positive derivative. What about the flip side of things? Well, on the flip side of things, if you have a decreasing function, so here's your increasing function, here's your decreasing function, b minus a, right minus left, is always going to be positive. So we got that's positive. But how about f of b minus f of a? What's going to happen when I subtract those? Yeah, you're going to get a negative. Now, a negative divided by a positive is still going to be negative. So that's going to equal something less than 0. So in other words, whenever f prime of x is less than 0, the function is decreasing. Kind of ran out of room there a little bit. My apologies. And that's great. That's a conclusion you get directly from the mean value theorem. Now there's a couple more things I'm going to lay on top of this, and I'm not going to go through the proof of it like I did here. But are we okay with these two conclusions? They're pretty consistent with what we've seen before, that when the derivative is positive, you regard that as being the slope of a tangent line and the function's increasing at that point. We're just generalizing it. Now, a couple of the things that we're going to add into this mix are the concavity. And that's going to be a little bit more of a nuance in terms of the shape of the function. Concave up is a function that looks like this. That's kind of a concave up shape. Roughly speaking, concave up holds water. So if you were to spill a cup of water into this, it would hold some of that water. Whereas concave down would be something like that. It's going to have a concave down shape, and that would spill water. Now this is very rough, but it does kind of give you a nice overview of what this looks like. Spills water. If you were to perform this kind of analysis with some functions, what you'll find is that f of x is concave up when f double prime of x is greater than 0. F of x is concave down when f double prime of x, fill in the blank for me, any guesses, any guesses? Yeah, thank you, is less than 0. So, all right. So knowing something about the derivative tells you a lot about the graph of the function. It tells you some of the nuances of the behavior of the function. Let's match that up with some actual graphs. And for that, let me go back to one of the examples that I gave you right at the start of this course. We're looking at the number of COVID cases in Oakland County a few years ago, etc. What kind of a shape do you think this graph is? Let me turn off the data. Let's just look at the graph. What kind of shape does that have? Is it concave up or concave down?
Concave up.
Concave up. So concave up means that you've got, right over here anyways, this function is increasing, but it's increasing at a faster and faster rate. So if you were the state epidemiologist, you'd be worried. It's like, okay, the number of cases, yeah, it's increasing, but it's increasing at an increasing rate. And that's bad news. You want to see this curve flatten out. And if you actually look at the data, it does look like it's starting to trend down. And where it changes concavity, where it changes its shape, that's an inflection point. We'll talk about those. Let's apply this to our first example. This one right here. This is a nice, friendly one. Polynomials are wonderful because they're so easy to differentiate, manipulate. You can make them go through any points you want. So let's apply this new information to this graph. So example A, we've got f of x equals x cubed minus 3x squared minus 9x plus 7. Okay, great. If I want to know where a function is increasing and decreasing, then what do I got to find? Oh, come on. First derivative, right? So f prime of x, I'm not going to bother you for this. That's pretty easy. There's your f prime of x. I'm going to want to know where that's equal to 0. What's going to tell me about the concavity? What do I need to know from here? Yeah, thank you, the second derivative. So f double prime of x is going to be 6x minus 6. And I want to solve both of these equal to 0. Well, the second of these, you could just move the 6 to the other side, divide both sides by x equal, or divide both sides by 6, and we get x equal 1. That's great. If I want to know where that's equal to 0 or does not exist, basically places where it can change signs, I can set it equal to 0. I'll factor out the x, or factor out the 3, and then continue factoring this. That's going to factor as x minus 3 times x plus 1. So I get two places. X equal 3, x equal negative 1. Now that in and of itself doesn't tell me a whole lot about the function. It's telling me where the derivative is 0. In other words, you got a horizontal tangent line, but it's not telling me where it's increasing or decreasing, concave up, concave down. So let's add a little bit more to this. I'm going to draw myself a nice little table. I suggest you do likewise. Actually, two tables. One for this one for this one. So we're going to write down a couple things. X, f, and f prime. Now my function was equal to 0 at a couple points. At negative 1 and 3. Okay. So we can do something like this. Yeah. Here, here, and here. I want to know not what's happening at those points, or not only what's happening at those points. I want to know what's happening at other places. The derivative here was 0, and the derivative here is 0. But what's going on in between these 2 points? What's going on to the right? What's going on to the left? Is the function positive? Is it negative? What's going on? Now it's up to you, but I'll give you a little reminder tutorial here on testing points. If I want to know where this is positive or where this is negative in terms of the sign of this function, then I can put that function into my calculator. So let me do that. Clear this old stuff out. Oh, I don't want to clear that one out. So what I'm going to do is I'm just going to shut this one off, because we're going to use that in, I think, our next example. So let me put in 3x squared minus 6x minus 9. That's my function. You can put yours in y1. It doesn't really matter so much. Our table setup should be like this. We've discussed that before. Hopefully that's not a big deal at this point in the course. Let's go to our tables, delete all these old points, start afresh. I need some points to the left of -1, between -1 and 3, and then to the right of 3. So I need some test points. Suggestions as to some test points. Yeah. -2 would work. 0 would work. 4. Those would be some good test points. So I'll plug those into my function. Actually, they're into the derivative. -2, 0, and 4. And you don't have to do this here. You can do it on, in your head. That's fine. So we ended up with 15, -9, and positive 15 again. Now, I don't care if I get 15 or 15 million. What do you think is the important part of information that I got out of this? Positive, negative, positive. Perfect. That's exactly what I was looking for. What's that tell me about my function now? This is your point, your part. Make me look good. What's that tell me that if to the left of -1 the derivative is positive? What's that saying about the function? It's increasing. So let's write a little up arrow like that. It's increasing there. Zaid, what's happening between -1 and 3? What's the function doing? Decreasing. Thank you. And then increasing again. Now I haven't drawn the graph at all, have I? I just drawn this little table. But this is a very wonderful little summary of what's going on with the function. You can kind of see and feel what's going on. So if the function is increasing and then has a horizontal tangent line and starts decreasing, what kind of a point does this have to be? If it's increasing and then starts decreasing, what happened in between? Where did you max out at? Well, I think I kind of gave it away here. You maxed out. You have a maximum point, right? If the derivative goes from positive to negative, this point has to be a maximum point. So that's a maximum. It's at least a local max. Local max at x equal -1. How about the story over here at 3? What's going on at 3? Yeah, you've got a local min. All right, at least a local min. Just going to depend on problems. Local min at x equal 3. Wow, that's kind of cool. Let's put that to the side for the moment. Let's work with the second derivative. So I'm going to draw a similar table. This time I'm going to label it f double prime. And let's see, I had 1. The second derivative at 1 was 0. But now I got to decide what's happening on either side of that. Now, I'm going to be working with the second derivative here, not the first derivative anymore. We're done with that. I don't think I need to put this one into my grafting calculator to test points. What's something to the right of 1? 2. All right. 2 works. 6 times 2 minus 6. I don't even care that it's 6. All I care about is that it is positive. How about to the left of 1? 0. If I put in a 0 there, what am I going to find out about the second derivative?
Negative.
It's negative. Now let's be careful about our conclusions here. We're no longer talking about increasing and decreasing. So, Louis, what's going on with the function if the second derivative is negative? Rebecca? Rebecca, some help? Yeah, concave down and then concave up. Where the second derivative is negative, you have a concave down shape. Where the second derivative is positive, you have a concave up shape. So, beautiful. Now this point where it changes concavity is called an inflection point. Inflection point. There's a series on Netflix, I think, I can't remember the title of it. A friend of mine was telling me about it the other day, where they talk about essentially inflection points in history. Like during the Vietnam War, the Tet Offensive would have been an inflection point. It changed the nature of the war. So let's take a look at the graph and start trying to make sense of some of these things that we're seeing here from our table on the derivatives. So let's see, I don't want that one yet. Let's take a look at this one. Here we go. So let's see, right here, you've got your maximum there, you got a minimum there, but the function is increasing until we get to x equal -1. What happens from -1 to 3? Oh, the function is decreasing. If you match that up with our information from our derivative, we had increasing, decreasing, then increasing. So far, this is looking pretty good. The function also changes its concavity. It'd be tough to look at these things and spot the exact point without knowing a little bit of calculus. It's tough to say, well, where exactly does the function change concavity? But we don't have to guess. That exact point is right down here at x equal 1. That's where it changes from concave down to concave up. So this is all matching with what we got. Now when you're asked for this information on a test or on WebAssign, you'd answer something like this. It's increasing on -infinity to -1 union 3 to infinity. It's decreasing on -1 to 3. Great. You've got a local max, you've got a local min. Let's take a look at the concave up and concave down. Concave up, that's going to happen at what interval? Someone want to fill that in? Nicholas, where's it concave up? Yeah, 1 to infinity. Awesome. And concave down? Eura? Where would be concave down? So to the left here, what interval would that give us?
-infinity to 1.
Yeah, -infinity to 1. Perfect. Our inflection point is at x equal 1. Great. So there's just a ton of information you can get out of this function by looking at the first and second derivatives. A lot more information than we saw in college algebra. Okay. Any follow-up on that one? All right. So I see where your excitement and energy level, that we need to make them harder. Cool. I got your back. So let's move on to example B. Example B is a little bit more challenging because we have trig functions. And I know that everyone's really friendly with trig functions, especially if it's been a bit since you've seen that stuff. So let's carefully go over that one together. And I'm also going to share with you some more tricks and reminders on your graphing calculator. So if you don't have a graphing calculator, make sure you borrow one. Let's move on to example B. We're going to look at what I call g of x is cosine squared of x minus 2 sine of x. And mercifully, we're going to limit you to the interval of 0 is less than or equal to x, less than or equal to 2 pi. Okay, great. Let's see here. Well, the big thing to understand with this notation is that it's really cosine of x squared minus 2 sine of x. Why am I pointing that out? What difference does that make to me? What rule do I have to use in differentiating this one now that I see it a little bit more clearly? The chain rule, right? The derivative of the outside times the derivative of the inside. So let's see here. G prime of x, Rebecca, maybe you can help me out. Derivative of the outside, 2 cosine of x, I'm not going to write to the first power, times the derivative of the inside. Negative sine of x, good. And the derivative of the second part of this is just going to be minus 2 cosine of x. Great. All right, so let's see if we can't clean this up a little bit. That's going to be minus 2 cosine of x, sine of x, minus 2 cosine of x. Now, back when we first started calculating derivatives, I gave you a heads up. I'm like, you know, you might want to practice cleaning things up because later on you're going to need to do that. Here's where we start needing to do that. So let's take a look here. I could factor out a minus 2 cosine of x. What's going to be left behind if I factor out that minus 2 cosine of x? How about for my first term? Sine of x. Yeah, and for my second term, you don't just leave a vacuum. Really, by factoring this out, you're dividing each of these terms by that coefficient or by that term. And when I divide this by itself, I get a plus 1. Why did I bother to do that? That's a good question. Eventually, you're going to have to set these things equal to 0 and solve, right? So if I set that equal to 0 and say, hey, well, I need to solve, then I need to figure out where this times this equals 0. I've got two options here. Either minus 2 cosine of x equals 0 or sine of x plus 1 equals 0. On the left, I can just divide both sides by negative 2 and get cosine of x equals 0. On the right, I'll move the 1 to the other side and get sine of x equals negative 1. To finish solving here, if you don't remember your unit circle very well, you could use the inverse cosine and the inverse sine. Be careful if you're doing that in radians because you might not recognize some of these angles in radians. So for instance, if I did inverse sine of negative 1, and my calculator is in radians that you can see, I don't know, how many people recognize that decimal value? It's not necessarily really easy to recognize. So if you wanted to put your calculator temporarily in degree mode, maybe you'll recognize that value a little bit easier. So I'll just do that one again. Now I get negative 90. Oh, okay, yeah, that makes more sense. And you can kind of verify that negative 90 is really negative pi over 2. Oops, over 2. Let's do divide by 2. Okay, and yeah, that matches up the decimal values. Put your calculator back in radian mode with all due haste so you don't make a mistake later. Typically speaking, we don't take our calculators out of radian mode. So that's one possibility. Is negative pi over 2. Actually, we want the interval 0 to 2 pi. Negative pi over 2 would also be the same thing as 3 pi over 2. So there's one possibility there. The other possibility is where the cosine of x equals 0. Cosine is what coordinate on my unit circle? X coordinate. Let me see if I can't just pull up a unit circle here for us real quick. That'd probably be my trig class. There we go. All right, so let's take a look at the unit circle. You're looking for a place where the x coordinate is 0. And there's really a couple places where that x coordinate is 0. One of them's right here, one of them's down here. So at pi over 2 and at 3 pi over 2. So basically, we're getting a little redundancy in terms of our solutions. So pi over 2 or 3 pi over 2. We get that one twice, no big deal. Those are places where the derivative is 0. So let's do ourselves a little favor here and make ourselves a chart. So x, g of x, and g prime, pi over 2 and 3 pi over 2. So these values are 0, so you expect a horizontal tangent here and here. You could plug this function into your calculator and test some points, test it, find it positive, negative, etc. But let me share with you some good news. I've already graphed some of these things for you. This is the graph of y equals g of x. Here's the graph of y equals g prime of x. And you can kind of see what we're already seeing, and that is that the function crosses the x-axis at these points at pi over 2 and 3 pi over 2. Let's see if we can't fill in some information about the derivatives just by looking at the graphs. So, okay. To the left of pi over 2, is the derivative positive or negative? Yeah, it's negative because it's below the x-axis. So let's put a negative there. And then between pi over 2 and 3 pi, the function is, or the derivative is positive. Then what happens to the derivative? It's negative. So negative, positive, negative. Does that match with the graph? Well, yeah. Because until we get to this point, the function is decreasing. And we see that with the derivative. The derivative is negative until we get to pi over 2. Then the function starts increasing until we get to 3 pi over 2. So the derivative is positive in that interval. And then the function starts decreasing again. So that perfectly matches this. All right, take out your calculators. Let's put those that function into our calculator, and then I want to show you a couple of tricks. Now, as far as putting that function into your calculator is not going to understand the notation that we understand. It's not going to understand cosine squared of x like that. You have to put it in as parentheses around the cosine and then square it. So that's going to be your cosine of x squared. And now I'm going to get a little bit lazy here. I know we've already calculated the derivative. I don't feel like programming in the derivative for myself. I'm going to let my calculator do it. So, everyone's got the function in, right? We're good there? All right, some nods. Thank you. Let's go to the math key. What do you see in the 8th option down? It's a numerical derivative. It's not going to tell you that the derivative of cosine squared is 2 cosine x sine x, but it can differentiate these things numerically. It can give you a numerical derivative, and it can give you a graph. So let's hit that. I want the derivative. What are we differentiating with respect to? X. So hit the x key. And I want the derivative of this function. So I don't really feel like typing in that whole function. Zaid's looking at me like, yeah, I'm with you, Jeff. I don't want to type in that whole function. So what could I do? Oh, let's go to the vars key. Hit the vars key, and then, oh, we have something in y. So go to the y variables. Y vars, and we want a function, so press enter. And there we go. Press enter again, and it's going to differentiate whatever happens to be in y1. Great. And to finish this off, to get a nice graph, just put an x there. And so that's going to differentiate this. You're going to end up with the graph of the derivative just as if we graphed the function that we calculated for the derivative back over here. Your graph there is going to match exactly what we have there. Let's see that. Now, as far as a window is concerned, what should I set my window at? Any suggestions? How about on the x-axis? Where should I go? 0 to 2 pi. And on the y-axis, look, just mimic my graph, right? You don't have to think too hard about it. My graph goes from -3 to 3 on the y-axis. So let's do that. So for my window, 0 to 2 pi. Now when you type in 2 pi, as soon as you hit enter, that nice comforting pi symbol is going to disappear and it's going to give you a decimal value. No big deal. X scale. Let's give ourselves a scale that would be helpful. I'm going to put tick marks at every pi divided by 2 units. That'll be a little bit more useful than every 1 unit or whatever. -3 to 3. Bam. There's your graph. That's the graph of the first derivative. Nice. How about the graph of the second derivative? By the way, did you guys get that one? Is that working out on your calculator? Got 1 or 2 nods? Not too many nods. All right. Thanks, Clyde. No? No?
I also have like an old calculator.
Yeah, you should be borrowing one of mine.
Okay.
It'll do it. It's just that the older 83s require a lot more love to do that. Yes?
What did we set x equals to?
So you mean over here? Set x equal to x. Yeah. Any other comments on that? So you're getting that graph? Now you might have both graphs. Let me go back and turn on both of my graphs. The nice thing about the up-to-date TI-84s is that they're in color. So you know which one's the function and which one's the derivative. And you can start matching things up. Like until we get to this point, the function is decreasing. And you can see that. The derivative, which is in red, that's below the x-axis, and it's decreasing until we get to pi over 2. And so on. Suppose you want the second derivative. All right, let's find the second derivative. Oh, wait. Let's kind of take a shortcut. If all I needed or wanted was the graph of the second derivative, let's go back to our math menu. Now follow along. Take out your math menu. Let's go down to 8 again. We're going to differentiate with respect to x. This time I don't want to differentiate the function. What do I want to differentiate? To get the second derivative, what should I differentiate here? y2. I'm going to differentiate y2. So vars, y vars, function. This time pick the second one down. So go down and press enter, or simply type the number 2. There's your y2, differentiate it with respect to x. So that I don't really confuse myself, I'm going to shut off the graph of the derivative. That's this one. Now this time I'll see the blue graph and the black graph, my function and second derivative. There we go. So a lot of changes in the concavity based on the second derivative. That's okay. Let me actually just kind of make my graph a little bit less busy here. I'll shut off the graph of the function. Where it's positive, the function is concave up. Where it's negative, it's concave down. And you have a little point here where it kind of flirts with changing concavity, but then it goes back the other way. So, wow. This is the graph of the second derivative here. Y equals g double prime of x. Now, I've actually calculated the second derivative and solved it here for you. You've got some points at pi over 6, at 5 pi over 6, 5 pi over 6, and finally 3 pi over 2. And in between, the function is concave down, concave up, concave down, and concave down again. So, okay, great. If you look back and compare this to the function, you'll see that it's got all those features. It's tough to find these points without calculus. I mean, if you're looking at this graph and saying, well, gee, is it concave up or concave down, just looking at the graph there, it almost looks like a straight line. It's impossible to tell that it's concave down there. It's concave down until we get to this point right here. That's where it changes concavity. Now all of a sudden it's concave up. And it's concave up there until we get to this point where it changes concavity again. Now how about at the last point? Is there a change in concavity at this point? Not really. It's concave down to the left and then concave down to the right. So there's no change in concavity. Where it does change concavity, these are inflection points. Inflection points. All right, wow, lots on that one. One possibility for me on an exam would be just to give you some graphs, and you know, they'd have obvious points or points that are labeled like I have here, and ask you for where a function is concave up and concave down, increasing, decreasing, mins, maximums, etc. So you can get a lot of information based on that graph. But where a graph changes concavity, that's an inflection point. Changes concavity. You're going from concave down to concave up, and then concave up to concave down. So overall, the function is concave down, starting from 5 pi over 6 to here. All right, I think we're going to get one, maybe two more in here. We'll do our best. Let's keep going. Move on to example C here. It says, consider the equation below. Find the intervals on which it's increasing and decreasing. Find local min, local max, concave up, concave down. All right. Probably a good place to start on this one is figuring out something about the domain. I forget whose question it was earlier. I think it was Derek's. I was talking about the domain of the log function. Do you remember what the domain of the log function is?
0 to infinity.
Yeah, 0 to infinity. This isn't going to be defined at 0. It's only going to be defined for positive values of x. So the domain is 0 to infinity. So the domain is 0 to infinity. Why is it important to note that to start? You don't want to be looking for inflection points, minimums, and maximums where the function is undefined. Some of your algebra might lead you there, but you can just ignore those points because the function is not defined there. So let's see what we can do with this one. Example C. F of x is x squared minus x minus ln of x. Let's first start by calculating the derivative, f prime of x. Krish, what's the derivative here going to be, please? Nice. 2x minus 1 over x. I'm going to need to differentiate this again. So, Marlene, suggestions. What could I do to make this a little easier to differentiate the 1 over x term?
Do x to the -1.
Yeah, x to the -1. Let's differentiate this again. F double prime of x. Russell, what do we got? What's the second derivative going to be here, please?
It's 2, then plus 1x to the -2.
Nice. 2 plus x to the -2. Let's keep in mind our domain here. Thanks, Russell. Domain is 0 to infinity. Let's see if we can't solve where this is actually equal to 0. So I'll work with the first derivative, f double prime, or f prime of x equals 0 when 2x minus 1 over x equals 0. I'd probably multiply both sides by x. Can anyone suggest why I'd multiply both sides by x? Yeah, cancel out the x in the denominator. That's going to give me 2x squared minus x minus 1 equals 0. We're not going to make a big deal out of factoring this. It has to start out with a 2x and an x. And then both of these have to be a 1. 1 times 1 is going to be a 1. But one of them is going to be positive, one is going to be negative. Which one's which? First one's negative. If you do a little mental calculation here, 2x times x is going to be my 2x squared. If this is negative, I'll get a minus 2x plus an x. That's going to make that middle term a negative x, and then a minus 1. So I get two solutions here. The first one is when x equals 1. Where's the second one? Where does that equal 0? Anyone? -1/2. Thank you. X equals -1/2. So great. That's the first derivative equal to 0. By the way, can anyone tell me something about this? Somebody said it here. Whispered it maybe.
We can ignore
We could ignore -1/2. Why is that? Yeah, it's not part of the domain. Thank you. So it's not part of the domain. We'll ignore that one. Let's work with f double prime of x equals 0. And that's going to be 2 plus x to the -2 equals 0. Okay. So that's going to be the same as 0 equals 2 plus 1 over x squared. If I move that to the other side, I end up with negative 2x equals 1 over x squared. Let's do the same trick that we did before. Let's get rid of the fractions here. Multiply both sides by x squared. I get negative 2x squared equals 1. What do you get when you solve for x? We can be really conscientious with the plus or minus in here, but there's something that should be disturbing you. Yeah, that equals 0 only in your imagination, right? These are imaginary numbers now, so we can ignore this. So, only imaginary solutions. Fortunately for you, that's not part of this calculus class. We're not dealing with calculus of complex numbers. So, wow, what's that saying? What's that saying is that the second derivative doesn't change signs at all. It's of one sign. So what I'll do oftentimes is something like this. I'll just pick an arbitrary point in the domain, like a 1. Doesn't matter what point. You can pick any point in 0 to infinity. If you plug that point into your first or second derivative, what's going to happen with it? Is it going to be positive or negative?
Positive.
Positive, right? I mean, just pick a point like 1 or 2 or 3 or whatever. So if you plug it in, it's going to be positive. If it's positive, what's that telling me about my concavity in this function?
Concave up.
Concave up. Completely concave up for all values of x. All right, well, that's cool. Let's take a look at this part over here. Now over here, we actually do have to pay attention a little bit. We've got one point where the derivative can change signs, and that's at x equal 1. At x equal 1, we've got a derivative of 0. But I need to test points to the left and to the right. And to kind of help things out of there a little bit, I'm not going to put this into my graphing calculator. I'm just going to give you some values off the top of my head. I think if I put a point in here like 10, that derivative is going to be positive. Over here, derivative is going to be negative. So I believe that the function would be decreasing, then increasing. If the function is decreasing, then increasing, what does that say about this critical point at x equal 1?
Local maximum.
The local maximum. Is it? It's decreasing and then starts increasing.
Local minimum.
Local minimum, thank you. So it's at least a local minimum. And if we look at the graph, I think it's going to be an absolute minimum. So x equal 1 is a minimum point. It's decreasing on on 0 to 1, and then increasing on 1 to infinity. And it's concave up on 0 to infinity. It's completely concave up. So we have a really good idea of what this graph looks like, even though we haven't graphed it at all. We know a lot of information about this graph. Let's just see, for sake of seeing it, how this graph actually matches up to our expectations. So let me shut, where is this one? Oh, there. Yeah, let's get rid of that one. And oh yeah, here it is. So there's your function. And what you can see is that it's concave up everywhere. You've got a minimum at 1, and that minimum is really an absolute minimum, and then it keeps on increasing after that. So it absolutely matches everything that we've got. Please don't rely too much on your graphing calculators to get you through these kinds of problems, because they're not going to tell you exact points and exact coordinates like we can get with algebra. All right, enough for right now.